The topic is Gauss-Seidel iteration method. It is also another iteration method of finding the solution of a system of linear equations. And the method is quite similar with the previous one, that is Gauss-Jacobi iteration method. Just there is only a slight change in the iteration procedure. So the preliminary condition of this method is the system should be strictly diagonally dominant. That is, the given system of equation should be strictly diagonally dominant. At first we need to make sure that is aii should be greater than summation of aij. Okay, obviously I not equal to j and j runs from 1 to n. This is the condition of strictly diagonal dominance. Now let us consider the system of equations as this: a11x1 plus a12x2 plus dot dot a1n xn equals b1, then a21x1 plus a22x2 plus n equals b2, and so on up to the nth equation as an1x1 plus an2x2 as dot dot ann xn equals bn. Okay, we have considered that this system is strictly diagonally dominant. Now from there get the value of x1. So it will be x1 equals 1 by a11, then in bracket b1 minus a12x2 minus dot dot minus a1n xn, right? Now from the second equation get the value of x2. So it will become x2 equals 1 by a22, then b2 minus a21x1, the next term will be minus a23x3 minus dot dot minus a2n xn. This one. Similarly from the nth equation get the value of xn. So it will become xn equals 1 by ann bn minus an1x1 minus an2x2 dot dot up to minus a n minus 1 xn minus 1. This one. Okay. Now for the iterative or iteration procedure, unlike like Gauss-Jacobi procedure, what did we do in Gauss-Jacobi procedure? We use k plus 1 over the left hand side for the k plus 1th step, and for the right hand side variable we use k. But here it is slightly different. For the first equation all the powers will be k, this one. For the second equation, the first component, that is for the first variable, it will be k plus 1. Okay, here the first variable is x1, so it will be k plus 1. All the remaining other terms will be k. This is the main difference of Gauss-Jacobi and Gauss-Seidel method. All the other procedures are same. So for the second equation, the first term having k plus 1th degree. So for the nth equation, first n minus 1th term will have the k plus 1 degree. Okay, so this is first term, this is second term variable term, and this is the n minus 1th variable term. So all of this will get the k plus 1 degree. Okay, so this is the difference. For if we do the third step also, then it will be clear. What will be x3? X3 will be 1 by a33, then b3 minus a31x1 minus a32x2 minus dot dot a3n xn, this one, right? So here the power will be, this will be k plus 1. This is the third equation. So first two terms will get the k plus 1 power. So this will be k plus 1 and this will be k plus 1. All the remaining other variables will get k. Okay. So similarly like this, for nth equation we get this one. This is the required iterative formula for Gauss-Seidel iteration method. Okay, and the condition for convergence of this procedure is exactly same as that of the previous one. The system should be strictly diagonally dominant. Okay, so now we are going to use this over some example. Solve by Gauss-Seidel iteration method. Solve by Gauss-Seidel iteration method. x1 plus x2 plus 4x3 equals 9. 8x1 minus 3x2 plus 2x3 equals 20. 4x1 plus 11x2 minus x3 equals 33. Okay, correct up to 3 significant figures. 3 significant figure. Okay, so the first and foremost thing is we have to check that this is strictly diagonally dominant or not. So check for the first variable, this is 1, so 1 should be greater than this plus this. Actually mod 1 should be greater than this plus mod 1 plus mod 4, but this is not true, right? 1 is not greater than 5, so the first equation is not strictly diagonally dominant. Let's check for the second one. For the second one, this minus 3, its modulus value should greater than this one and this one. So mod of minus 3 should greater than mod 8 plus mod 2. No, this isn't true at all. So this is also not true. Similarly, the third one will also not be true. That means we need to change the position. Okay, now where will we change? Which equation should we make as the first one, as the third one, or the second one? Which one? Now check for the first equation. Which is the largest coefficient here? This 4 is the largest coefficient. 1, 1, 4. So as 4 is the largest one, that is the third position is the largest one. So if we keep it as the third equation, then for the diagonal dominance checking, we need to prove that this mod 4 should greater than mod 1 plus mod 1, which is obviously true. So we put this in the third position. Now check for this equation. Which is the greatest coefficient? 8. Mod 8, mod 3, mod 2. Among these, 8 is the greatest one. So the first coefficient is the greatest one. That means if we put this in the first position, then for the checking for diagonal dominance, it will be easier to show that mod 8 is greater than mod 3 plus mod 2. Okay, so we are rewriting the equations as x1 minus 3x2 plus 2x3 equals 20. 4x1 plus 11x2 minus x3 equals 33. x1 plus x2 plus 4x3 equals 9. Okay. Now check. Mod 8 is greater than mod minus 3 plus mod 2. This is true. 8 greater than 5. Next, mod 11 is greater than mod 4 plus mod of minus 1, which is equal to 5. Right? Next is mod 4 is greater than mod 1 plus mod 1. So the system becomes strictly diagonally dominant. Now we can apply Gauss-Seidel procedure. So from the first equation, what did we get? x1 equals 1 by 8, 20 plus 3x2 minus 2x3. This one, right? Next, from the second equation, x2 equals 1 by 11 into 33 minus 4x1 plus x3. And from the third equation, x3 equals 1 by 4, then in bracket 9 minus x1 minus x2, right? Now apply iterative method over it. So k plus 1, for the first equation, its all variable will be k. Then for the second equation, this is k plus 1, and for first variable we will get k plus 1. So this is k plus 1, and for the remaining one will become k. So this is k. Now for the next equation, which is the third equation, so first two variables will be k plus 1. Here are only two variables, so it is k plus 1, it is k plus 1. Okay, this is our required iterative formula. Now we need to put the values of k one by one and get the result. Okay, for the initial value, that is x1 to the power 0, x2 to the power 0, x3 to the power 0, we will take it as 0, 0, 0. So let x1 0, this equals 0, x2 0, 0, x3 0, 0. Okay, now put the value for k equals 1, k equals 0 for the first step. So it will become x1 to the power 1, so 1 by 8 into 20 plus 3 into 0 minus 2 into 0. That means ultimately 20 by 8, which is equals 2.5. Then x2 1, it will become 1 by 11, then 33, and the remaining terms will be minus 4 into x1 to the power 1, which is equals 2.5, plus x3 to the power 0, that is 0. So it will become 33 minus 10 divided by 11, that is 2.0909. Okay, next x3 to the power 1, this will become 1 by 4, 9 minus x1 to the power 1, that means 2.5 minus x2 to the power 1, that is 2.0909. So after calculating, what will we get? We need to check up to 3 significant figure, correct up to 3 significant figure. Okay, so 1.1023. Here we have taken up to 5 significant figure. You can take up to 4 also. So this is 1.1023. Okay, this is the first step for k equal to 0. Now moving to k equal to 1. K equal to 1. So it will become x1 to the power 2 equals 1 by 8, 20 plus 3 into x2 to the power 1. x2 to the power 1 was 2.0909 minus 2 into x3 to the power 1, that is 1.1023. It will become 3.0085. Okay, next x2 to the power 2, so it will become 1 by 11 into 33 minus 4 into 3.0085 plus 1 into 1.1023. Its value will be 2.0062, right? Next, x3 to the power 2, that is 1 by 4 into 9 minus 1 into 3.0085 minus 1 into 2.0062, and it will be 0.9963. Okay, now check the values with the previous step. At first check the x1 values. In the previous step the value was 2.5. Here it is 3.0085. So it is not same at all. It is quite equal to 3, and that was equal to 2.5. So this step cannot be the terminating step for at least x1. So no need to check for x2 or x3, because this is not the terminating step for x1. So we cannot terminate the procedure here. So moving to for k equal to 2, it will become x1 to the power 3 equals 1 by 8, then 20 plus 3 into the previous steps values, that is 2.0062 minus 2 into 0.9963, which is equal to 3.0032. Next next x2 to the power 3. So it will become 1 by 11 33 minus 4 into 3.0032 minus plus 1 into 0.9963 equals 1.9985. Then x3 to the power 3 equals 1 by 4 into 9 minus 1 into 3.0032 minus 1 into 1.9985 equals 0.9995. Now check the value. In the last step, x1 was 3.0085. So if you rounded it, you will get up to 3 significant figure. You will get it becomes 3.01, right? And for this step, x1 is 3.0032. Now if you make it rounded off, it will get 3.00. That is ultimately 3, right? So 3.01 and 3. These are not same. There is a slight difference of 0.01. So we need to check for the next step also. Now let's check for x2 and x3. That was the previous value. If you rounded it off, you will get 2.01, right? And for this step, you will get, this is our x2 for the current step. If you rounded it off, you will get 2.00. That is ultimately 2. There is also a slight difference of 0.01. So we need to move to the next step. Hopefully the next step will be the terminating step. So k equals 3. In that step we will get the value of x1 to the power 4. I am not writing all the one. The value will be 2.9995. Then x2 to the power 4, it will be 2.0001, and x3 to the power 4, it will be 1.0001. Now if you rounded it off, it will become 3.00, which is equal to the previous step's result for x1, right? So this is the value for x1. Next, if you rounded it up to 3 significant figure, you will get 2.00. This is also same with the previous step's result. And for x3, if you rounded it off, it will become 1.00. Let's check the x3's previous step's value. That was x3, 3. That is previous step's result. This one. If you make it rounded off, you will get obviously 1. So the values for 2 simultaneous steps are same. So this is actually the value of x1, x2, x3. 3, 2 and 1. Okay. Correct up to 3 significant figure.